Good morning to all. So, as I told you in the last session, today we will first see some examples related to the memory management techniques which we have already discussed. So, these kind of examples are important and frequently asked in many competitive exams as well. So, today we will first spend time on solving few examples so that you know the overall methodology if any such example is asked, and later on we'll try to complete the remaining topics from the virtual memory chapter. So let's start with the first example. So in the first example, this example is based on the page replacement policy, LRU policy. So just a quick revision of LRU. So what is page replacement policy is when you have to load some pages into memory and memory is already full, so you have to select one page from the current pages and swap it out and bring some another page in. This process is called page replacement. So we have seen various page replacement policies, and one of the policies LRU, that is least recently used policy. So in least recently used, what we do is we see the past behavior and select the page which was least recently used in past, and that we select for the replacement. So in this example, you see that there are 4 page frames, right? There are 4 page frames. So let me draw the structure. Is something like this. Okay. There are 4 page frames. So at each timestamp, we have to see the structure of the page. So first of all, it says that your memory can hold 4 page frames. So you can see that I have made 4 sections, 1, 2, 3, and 4. Okay. Initially, it is empty. So this is the initial state at time t equal to 0. This is the initial state. We are using LRU policy, as I discussed. The page reference string is given here. You have to determine the page fault rate. Okay. You have to determine the page fault rate, which is defined as ratio of number of page faults divided by total number of memory accesses. Okay. So you have to find out number of page faults divided by total references. Okay. So initially it is empty. So new request is 7. You see 7. So 7, earlier it was not there in the memory and you required it. So it is a page fault. So you have page fault number 1 here. Next is 2. So 2 is also not there and we are bringing it in to the second page fault. Then 2. Then again 7. But this 7 is already there. So we don't need to do anything. Then 3. So 3 is not there in the memory. We are bringing it in. So again there is a page fault. So 3. Then 2. 2 is already there in the memory. We don't need to do anything. Then 5. So 5 is not present in the memory and we have to bring it in. So again it's a page fault. So we are bringing in 5. So this is the situation. Now next is 3. So 3 is already here in the memory. We don't need to do anything. Next is 4. So again, 4, if you check, is not there in the memory. So we have to bring it in. So there is a page fault. So I am just highlighting here and also counting the page fault. So now we have to do the replacement. So I have to swap out one of the pages from 7 to 3 and 5. Okay, I have to select one page from 7 to 3 and 5 for the replacement. So for that you have to scan in this manner. So which page was recently used? 3. So you cannot swap it out. Then 5, then 2, and then 7. 7, if you see, it was used least recently. I mean, it was used long time ago. In comparison with 3, 5 and 2, 7 was least recently used. So I'll swap out 7, and in place of 7, I will put 4. So new allocation will be 4, 2, 3 and 5. So this is done. Now next is 6. Next is 6. So 6, if you see, is also not there in the memory. So it is a page fault. So I have to count the page fault and I'm highlighting it for your reference. Now you have to swap out one page from 4 to 3 and 5 and bring 6 in. So if you scan in backward direction, you see 4 was used recently, then 3 was also used, then 5 was used, 2 is least recently used. Okay, 2 is least recently used. So I'll swap out 2 and instead of 2, in place of 2, I'll bring 6. Okay, so this will be my new layout 4635. Okay, next reference is 7. So again, 7 you can see is not present in the memory. So it is a page fault, is a page fault, and I have to select one page for replacement from 4, 6, 3 and 5. Okay, from 4, 6, 3 and 5 I have to select. So 4 was recently used, then 3 was used, then 5 was used. Oh sorry, 6 was used, then 4, then 3, and 5 is least recently used. I hope you are getting the overall algorithm. You have to just scan left side. So 6, 4, 3 and 5, if you see, it was least recently used. So in place of 5, we will bring 7. So now other frames will remain as it is. So again, this is one page fault. Then again 7. So 7 is already there, so no need to do anything. Then 1. So 1, if you see again, 1 is not present in the memory. So it is a page fault. I am counting a page fault. And I have to swap out from 4, 6, 3 and 7. From 4, 6, 3 and 7, I have to swap out. So if I see 7 was recently used, then 6 was used, then 4 was used. 3, if you see, it is least recently used. So 3 is least recently used. So I will swap out 3 and instead of 3, I'll bring 1. So now 1 is like this. Okay. Next is 5. So again 5 is not present. So I have to swap out. So again it is a page fault. Okay. The page fault. And I have to scan 4, 6, 1 and 7. So 1 is used recently, then 7, then 6 and then 4. So 4 is the oldest. 4 was least recently used. So I have to swap out 4 and in place of 4 I will bring 5. So 5, 6, 1 and 7. Okay. Next is 6. So 6 is already there in the memory. Don't need to do anything. And 1. 1 is also present in the memory. You don't need to do anything. So this is my last state or final state. 80 equal to how many times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right? So at 15 time, this is my state of the memory. And now I have to count the number of page faults. So as per this formula, how many page faults I uh, encountered totally, that divide by 15, because 15 is the total number of references. So if you see 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 divided by 15. Okay. 9 divided by 15. That is my page fault rate, and it's equal to 0.6. So here the answer is 0.6, the page fault. Okay. So this is the example related to page replacement policy. I encourage all of you to try the same example using FIFO and clock policy as well. Okay. So repeat the same example with FIFO and clock policy and determine the number of page faults in each. So you can refer the last lecture for more details on FIFO and clock policy. So in this way, this kind of examples can be asked where you are given the page references and you have to calculate the page fault rate. Okay. So that was the first example which I wanted to discuss. Let's take a second example. Okay. Now the second example is read the data. The second example. So it says that consider a system with byte addressable memory, and you have a 32-bit logical address. You have a 32-bit logical address. The page size is 4 KB and the page table entries are of 4 bytes each. The size of page table in the system in MB is dash. So you see this kind of examples where the logical address, physical address, page size, page table entry size is given, what you are supposed to do. So first thing is you have to interpret the given data, right? Whatever data is given to you, that you have to interpret. So you can see the logical address, as you know. I see the format of logical address is this, right? Page number and offset, right? The structure of the logical address is page number and offset. So here 32-bit address is given and the page size is 4 KB, right? Page size is 4 KB. So what is 4 KB? It is 4 into 2 raised to 10, that is 2 raised to 12. So because page size is 2 raised to 12, 12 bits are used for offset. 12 bits are used for offset and the remaining bits are used for the page number. So I can say that 20 bits are used for page number. Okay. Now we have to find page table size. So what is page table size? See, page table is like this, right? Page table is like this. For each entry, it contains page table entry, right? So page table size is basically number of page table entries into size of page table entry, right? So like if I have 4 page table entries and size of each entry is X, then the size of the page table is 4 into X, like this. Okay, very simple. Now if you observe the given data, the size of the page table entry is already given to us, that is 4 bytes, right? So it is already given to us, this is 4 bytes. Number of page table entries that we have to determine, number of page table entries. So from this logical address, you can see that page number field, the page number field is of 20 bits, right? The page number field is of 20 bits. So how many page table entries are possible? 2 raised to 20, right? Because for each entry, you need 20 bits. Because what is this each entry? It is giving you the page number. So since the page number is represented by 20 bits, for each entry you require 20 bits. So total number of page table entries will be 2 raised to 20 into size of page table is 4 bytes. So what is the answer here? Is 2 raised to 22 bytes, or 2 raised to 20 into 4, right? MB. Sorry. So this is equal to 1 MB. This is equal to 1 MB into 4. So the answer is 4 MB. The answer is 4 MB. So here the answer will be 4 MB. So you have to understand this structure. Again, if you don't understand if you feel that you don't understand it, you need to revise the topic of address translation in simple paging. Okay, if you refer the address translation, then it will become more clear if you are not understanding. But you have to keep the basics in mind. Logical address contains page number and offset. From the page number, you go to page table and find out the corresponding frame number. And frame number, if you append with the offset, you will get the physical address. So this flow you have to set in your mind, and accordingly some data is given, some data will be missing. So if you interpret in that way, you will be able to get the answer. So this was the second example which I want to discuss. Okay, let's take the third example. The third example says that in a virtual memory system, size of virtual address 32 bit. Size of physical address is 30 bit. Page size is 4 KB, and size of each page table entry is 32 bit. The main memory is byte addressable. Which one of the following is the maximum number of bits that can be used for storing protection and other information in each page table entry. So a lot of data is given, but the example is very simple. But first, let me put the basics here. So what happens in virtual memory? Again, you have this virtual address. So virtual address again has page number and offset, right? From page number, you look at the page table. Now each page table entry contains two parts. One is frame number, right? It's a mapping that where in the main memory this page is located, right? So it is giving you the detail of a frame number, and the other part is storing the protection and other bits. I would say protection and other control bits, right? So very simple. Here, this part which I have marked in question, that you have to find out. In this example, it says that how many bits we can use maximum way for storing this protection and other control bits. Okay. So let's see the given data. Now at the other end, I also have physical address. How does the physical address look like? Physical address looks like frame number and offset. If you see, frame number is also given. It says that physical address is 30 bit and page size is 4 KB. Okay, page size is 4 KB. So what is the meaning of 4 KB? Page size (4 KB) is equal to 2 raised to 12. So it means 12 bits are used for offset. Always remember this concept, that whenever page size is given, okay, whenever page size is given, you have to convert it into number of bits, and those bits will be useful for offset. Okay, those bits will be used for offset. So here say that the total address is of 30 bits. Out of that, 12 bits are for offset. So remaining 18 bits are for the frame number. Okay, remaining 18 bits are for the frame number. So now the things are very clear, right? Since the frame number is of 18 bits, here also you require 18 bits. And what is the size of the page table entry? Is given somewhere. The size of each page table entry is 32 bit. Size of each page table entry is 32 bit. So this data is of 32 bits. Out of this, 18 bits are used here. So what are the remaining bits? Remaining bits are 14. So the answer is 14 bits you can use to store other information. Okay. See, this is very simple. Page, what is the purpose of page table? To store one thing is essential, frame number. Okay. It has to store the frame number. Okay, it can store it, and remaining things, whatever bits are remaining, those bits we will use for storing the other bits or other control information. So here, out of 32 bit page table entry, 32-bit page table entry. 18 bits are used for frame number, and the remaining 14 bits are used to store the other information. So you can see that with the given information, from each information you infer something, and you can find out the remaining things. But you need to keep this flow in your mind, that from virtual address to page table, from page table to physical address. And always remember that 1K is equal to 2 raised to 10. Okay, is equal to 2 raised to 10. So when I say 4K, it is 2 raised to 12 bytes. Okay. So this is the third example which I want to discuss. Next. Okay. Now the next example is based on the concept of multi-level paging. It is based on multi-level paging. So I think you already know what is multi-level paging, which we have already discussed. So what happens in multi-level paging? See, normal scenario, what happens from your virtual address, you find out the page number. That page number is there from the page table. You find out the physical address. That is what you require. But sometimes what happens is the page size, the page table size is very large. So instead of a single page table, what we do, we kind of divide the page table into multiple levels. So first level of page table will point to other second page table, third page table, like that. For example, if I say like this, it has 5 bits, the first page table L1. So it means that each entry in the first level of the page table points to 2 raised to 5 entries in the second page table, like that. This is the second page table. Then let's say here the size is 5 again. So here also each entry corresponds to 2 raised to 5 entries. So total we have 2 raised to 10 entries in the page table. But instead of 2 raised to 10, what we have done, we have splitted across 2 levels. So this 2 raised to 10 bits are splitted across the 2 levels, where the first level index is first 5 bits and the second level index is the remaining 5 bits. And we have discussed that while going through the theory, we discussed that it is just like your index of a book. If the index of the book is very large, what you do is you divide your index into index. So there is the index of index, then there is the index of index of index, like that. So in that way, multi-level page table or multi-level paging works. So based on this, we have an example. So consider the computer system with 57-bit virtual address using multi-level pre-structured page table with L levels of virtual to physical address translation. So just like in my example, I have 2 levels. like that here L levels. The page size is 4 KB. Again, it's a very popular page size. And page table entry at any level, it occupies 8 bytes. It occupies 8 bytes. So again, we have two data given. One data is in terms of virtual address space. So let's plot this. So virtual address space is 57 bit long. Okay, 57 bit long virtual address, right? L levels are given. Okay, page size is 4 KB. So page size that means 2 raised to 12 bytes. Okay. So 12 bits are used. 12 bits are used for offset, and 57 minus 12, that is 45 bits are used for page number. Okay. So ideally, we should have a page table with 2 raised to 45 entries. Okay. Ideally, our page table should be 2 raised to 45, but we are not using it. We are dividing into L levels. So we have to determine these number of levels. So our one more data is page table entry at each level. Hello. Page table entry at each level is of 8 bytes. That's equal to 2 raised to 3, right? Equal to 2 raised to 3. Now we have to find out that each page table contains how many entries, and according to that we can find our splitting. Okay, according to that we can find our splitting. So how many page table entries are there? So number of page table entries remember this formula, very simple, is number of size of page, because you want to access a page, right? You want to access your page with the page table entry. So size of the page divided by size of each size of page table entry. So what is the size of page? Size of page is 2 raised to 12, and size of page table entry is 2 raised to 3. So here answer is 2 raised to 9. So number of page table entries at each level, okay, because you don't have one level, you have L levels, but at each L level, the number of page table entries are 2 raised to 9. Okay, it means 9 bits are used to get your page table. So total how many bits we have? 45. And at each level we use 9 bits. So how many levels we can use? 45 divided by 9, that is 5. So we can use 5 levels of paging if our number of page table entries are 2 raised to 9. Let me break it down more. So your virtual address will look like this. Definitely these 12 bits are used. So this first 9 bits, second 9 bits, third 9 bits, fourth 9 bits, and fifth 9 bits. So like this, you have 45 bits and the remaining is your page offset. Okay. So from first level, you get 2 raised to 9 entries. Then each 2 raised to 9 entries points to other 2 raised to 9 entries in the second level. Then the second level points to 2 raised to 9 level and of third page table. Like that, 2 raised to 9 into 2 raised to 9 into 2 raised to 9, 5 times. If you multiply, it will be equal to 2 raised to 45. Okay, that means your 45 bit address. So very simple and crucial uh, step here is to find this number of page table entries. So how you can find number of page table entries? You have to remember uh, that it is equal to size of your page, because from page table entry we want to find the page, right? We want to find the page. So size of your page divided by size of the page table entry. Suppose you have 10 pages and size of your page table entry is 2. So it can have 5 entries like that. If the size of the page table is 5, page table entry is 5, then it can have only 2 page table entries. So this is regarding your multi-level paging example. And now the last example which I want to discuss is based on TLB. Okay, so I have what I have tried is that I have taken example of each segment, like normal paging, virtual memory paging, multi-level paging, page replacement policy, and then also I have TLB. So TLB, if you remember, let's discuss revise this concept. TLB. TLB stands for translation leukocyte buffer. It is a cache of page table entries. So when you try to convert your logical address into physical address, first, instead of searching page table, you search the TLB. Okay? Instead of searching page table, you have to search TLB, and from TLB, if you can find the page table entry, then you can directly form the physical address. If you are not able to find the entry from TLB, then you have to look at the original page table, and then even if you cannot find your entry from original page table, then you have to look for the secondary memory. Like that we have seen the flow chart. Now let's see what this example wants to convey. So it says that assume that in a certain computer the virtual address is 64-bit long. So always whatever data is given, just interpret it. So virtual address 64 bits long. Physical address is 48 bits long. Okay. Physical address is 48 bits long. Memory is word addressable. So it means you have to convert everything in terms of word. Okay. I'll come to that. The page size is 8 KB and the word size is 4 bytes. Okay. We'll see this data. The translation leukocyte buffer, or the TLB, in the address translation path has 128 entries. Right? So as I told you, there is a TLB. So in between this address translation, there is a TLB. It contains 128 entries. Okay, this TLB contains 128 entries. at most how many distinct virtual addresses can be translated without any TLB miss. Okay, so if you remember, there was a concept of TLB hit and TLB miss. What is the meaning of TLB hit? Is that whatever address you are looking for, that address you are able to find from the TLB itself. That is called TLB hit. And if the address that you are looking for you cannot find from TLB, it's called TLB miss. So here it says that how many addresses at most you can form without TLB miss, right? So in best case, how many addresses you can form directly from the TLB? That is what is asked. Now let's break down everything. So first thing is word size is 4 bytes. So what is page size? Let me write the data here. Page size is 8K. But since, so what is 8K? 8K is basically 2 raised to 13, right? 2 raised to 13. But word size, so this 2 raised to 13 bytes, but word size is 4 bytes. So page size in words, page size in words is equal to 2 raised to 13 by 2 raised to 2, that is 4, is equal to 2 raised to 11. Okay, in words, because one word is equal to 4 bytes given, right? One word is equal to 4 bytes. So you have to find everything in one unit, and here the unit of addressing is bytes. Unit of addressing is word. Okay. Similarly, what is the virtual memory size? 2 raised to 64. Okay, it is 2 raised to 64. Now, how many pages are possible? Right? How many pages are possible? So out of this 64, 11 bits. So 2 raised to 11 is the page size. So as per our logic, 11 bits are used for offset. Okay, 11 bits are used for offset, and 53 bits are used for page number. 53 bits are used for page number. So this data we can interpret. Now, as you know, TLB, so TLB at a time can contain 128 entries. That means 2 raised to 7, right? Number of entries in TLB is 2 raised to 7. Okay. Now, if a page is found from TLB, then there will be a success, right? What do you mean by success? It means that, see, one page has 2 raised to 11 words, right? Remember, one page has 2 raised to 11 words. So if I say that there is a TLB hit, okay, there is a TLB hit for one page because it works in page levels. So there is a hit for one page. It means there is a hit of 2 raised to 11 words. Or in other words, all words of that page are able to be formed from the TLB. Okay. So at max, see, one page if you find from TLB, it means 2 raised to 11 addresses you can form. Okay, because each page has 2 raised to 11 addresses. if you find 2 pages from TLB, you will be able to form 2 into 2 raised to 11 addresses. If you find 3 pages from TLB, you will be able to form 3 into 2 raised to 11 addresses. So likewise, how many pages are there in TLB? As we know, TLB contains 2 raised to 7 pages. So if all those 2 raised to 7, because it's given as best case, right? In best possible case, how many addresses you can find from TLB? So in best case, you can find all 2 raised to 7 pages from TLB, and for each page you can have 2 raised to 11 addresses. You can have 2 raised to 11 addresses. So this many addresses you can form from TLB. You can form this many addresses from the TLB. So if I translate this into 2 raised to 18, it simply means this option. If you see, 256 into 2 raised to 10, right? 2 raised to 10 into 2 raised to 8, and 2 raised to 8 is equal to 256. So I can form 256 addresses. 256 into 2 raised to 8 addresses, or 256 into 2 raised to 10 addresses from TLB. Okay, this is at max and in the best case. So in the best case, it can find this many addresses from the memory without any TLB miss. Okay, so that is one more example. So this is the end of all the examples which I wanted to discuss. So along with this slides of lecture, I'll also circulate this as a PDF. So you may want to refer it later on if you want. So similar examples are asked in the exam. First thing is you have to see the number of bits, words, and draw this layout of virtual address, physical address, page table, TLB, etc. Then just you have to put the bits accordingly one by one, and you will get the answer. Okay. Okay. So now let's discuss remaining few remaining aspects of virtual memory chapter in the remaining time. In the last lecture, if you recall, we have discussed the concept of page buffering. So what is the meaning of page buffering? In page buffering, so usually what happens is when you require some page, you bring it from the memory. If it is not present in the memory, you have to generate a page fault and get it from the secondary memory. So in page buffering, what happens is you can do the page buffering and bring in some pages to the memory in advance. On the other way of implementing it is you use the FIFO algorithm, and whenever there is a page replacement, like today we have seen the example, you are swapping out the page, but in case of page buffering, you are not actually swapping it out. In page buffering, you are not swapping it out actually. Instead of swapping out, you maintain it in one other data structure, which is called free frame and use frames. So in one of these structures you put your page. So what is the benefit if you do like this? The benefit is that later on, if you want these pages back, then you don't have to generate a page fault, and you can directly get it from one of these lists. So here the list is just classified based on the nature of the page. I mean, if the page is not modified, then you put it in the free page list. If it is modified, then you can put it in the modified page list. So like that, you can bring the page immediately to the memory without the use of secondary memory, and that way the performance is improved. But the performance is improved only through increasing memory, because for buffering you require some memory, right? For buffering you require some memory. So page buffering comes at some cost. Okay. So the next topic is resident set management. So what is the meaning of resident set? Meaning of resident set is very simple. It's a number of pages of the process which are there in the memory. Number of pages of the process which are there in the memory, those pages, the set of those pages is called resident set. So OS must decide how many pages should be brought into the main memory. Suppose a process has 50 pages. So out of 50, how many pages you should bring in to your main memory in order to start the process? So if the smaller amount of memory is allocated to each process, its benefit is that more processes can reside in the memory, right? Because if the process amount is smaller the amount of the memory to the each process, so more processes can come. But it also means that a smaller number of pages are loaded, which increases the page fault. And beyond a certain size, further allocation of pages will not affect the page fault rate. So there are two options for the resident set size. The first alternative is called fixed allocation. The meaning of fixed allocation is what? Given a process, it gives a process fixed number of pages within which it has to execute. So suppose you have process A. Now I make a rule that for process A, maximum 10 pages should be loaded into the memory. Suppose process A has 50 pages, process A has 100 pages, but I say that at a time only 50 pages, only 10 pages should be loaded. That number 10 I am fixing. So that's called the fixed allocation. The second type of allocation is called variable allocation. So in case of variable allocation, the number of pages allocated to a process varies over the time. It means that you give a flexibility. You tell the process that, okay, right now you load 10 pages, then if required you can load 12 pages, if required you can load 15 pages according to your requirement and according to the other parameters such as page fault rate. So these two policies are there. Also along with this, you have scope of replacement, right? So you have scope of replacement. So scope of replacement can be global or local. The scope of replacement can be global or local. What is the meaning of this? So in case of local replacement policy, when the page is to be swapped out, the page is swapped out of the process which is generating a page fault. Okay. So suppose there are 5 pages in the 5 processes in the memory. Okay. Suppose there are pages of 5 processes in the memory. Let's say A, B, C, D, E. Now suppose process C is generating a page fault. Process C is generating a page fault. So if process C is generating a page fault, then one of the pages of only process C has to swap out. One of the pages of process C has to suspend. So that's your local replacement policy. In case of global replacement policy, it considers all unlocked pages in the main memory. So in that case, it is more flexible, but also you can say that's kind of dangerous. Why? Because let's say same process C wants to process C has generated a page fault. So what may happen that swap out the you may swap out the uh, page of process A also, even if process C has generated a page fault. You can also swap out the page of B. So you may argue that A and B are not generating page fault, then also why they are swapped out. But if the replacement scope is global, then it may be possible. So you can generate 4 different combinations uh, from these 2 parameters. So resident set size can be fixed or variable. Resident set size can be fixed or variable, and the replacement scope can be local or global. So based on this, I can generate 4 combinations: fixed allocation, local scope, fixed allocation, global scope, variable allocation, local scope, and variable allocation, global scope. So these 4 possibilities I can have, and each one has some implications. So let's see the summary. So if you see, first is fixed allocation, local replacement. It means the number of pages allocated to a process is fixed, but the replacement scope is local. So in that case, number of frames allocated to the process is fixed, and a page is to be replaced is chosen from the frames allocated to that process only. So it is one scheme, fixed allocation and local replacement scope. Variable allocation and local replacement scope. In that case, number of page frames allocated to the process is variable in nature, and the replacement scope is local. The third possibility is variable allocation, global replacement. That may be, better for most of the scenarios, because the allocation is variable. So if a particular process is suffering from page fault, then if a particular process is suffering from page fault, then it can increase its resident set size, and also the scope of replacement is global. One more combination is not possible. Remember that fixed allocation and global replacement is not possible, because if you are having global replacement, then you cannot have fixed allocation, because what will happen, it may be possible that all pages of your process may be swapped out due to the fault generated by other process. So your process may have to uh, unexpectedly terminate. So that's why this kind of scope is not possible. Fixed allocation and global scope is not possible. So from this discussion, there is one more concept of working set. So what is the purpose of working set? So working set is basically the concept which is used for deciding residence set size, right? So as you know, residence set, what is residence set? Residence set is number of pages of a process that should be present in the main memory. So how many pages should we bring in to the memory? This kind of decision is taken by the working set method. So working set method is very simple. For that we define a working set T comma delta. So working set of T comma delta is the set of pages of the process referenced in last delta time units at a specified time T. Okay. So from this working set method, we are able to decide our residence set. So if I am at time t equal to 5, for example, and if my delta is 3, okay, then I will look at time t equal to 4, time t equal to 3, and time t equal to 2, right? Because delta is 3. So I have to look 3 times back and then find out the number of pages which are referenced during that time. And that becomes my working set. So again, you see that it's similar to LRU, similar to what do you say, principle of locality, that whichever pages are referenced in past timestamps that you are referring. Okay. So this is the example of working set. Here at time t1, this is my reference. At time t2, this is my reference. So if I am at t1 delta 7, so I have to select all the pages. For t2 delta is 4, so I have to select the pages which are referenced during last 4 time units. Okay. When I say WT2 comma 4, it means that I am at currently time T2. I am currently at time T2, and how many pages were referenced in last 4 time units? How many pages were referenced in last 4 time units? That is my working set. What is working set method? So as you know, delta defines the window size. It's called window size. Large window size may result in larger working set, because if you are saying delta is equal to 5, so you are looking at 5 time units all the time. And also working set is a function of time. So if more pages are referenced during a period of time, working set will grow in size. And if same pages are referenced frequently again and again, the same pages are referenced again and again, then nothing will change. Working set will remain as it is. There will be very less changes in the working set. So this is the overall behavior of the working set. So you can see that during the execution of the process, there comes some periods where working set grows and then again becomes stable, then again it grows, again it becomes stable, right? So this phase of growing a working set, this phase of growing, it means change of locality. Means that whenever new addresses are being generated, okay, whenever new addresses are being generated over the period of time, so during that time the working set will grow, then again the locality will stable. So it means that the page references will be again from the similar locality. So that's why working set will working set will be stable, and then again it will go up and like that. You can see the working set method. Initially the number of page reference is high and process should stabilize later due to principle of locality, as I discussed that because now you are generating addresses from the same range. Okay, you are generating the address from the same range, so that's why it will stable. But again, as I discussed, this locality will be shifted to new locality after some time, and working set size will increase. Again, it get decreased, and only the pages of new locality are kept. Okay. So if you want to apply this working set method, what you can do is you can monitor the working set of each process. Okay. For each process, you have to monitor the working set, periodically remove the pages which are not in the working set, right? So working set will keep getting updated, and you have to periodically see that whichever pages are not in the working set, those pages you have to swap out. So this periodically remove means you have to swap out. So swap out the pages which are not in the working set. A process can only be executed if its working set is present in the main memory. So now you are reducing the scope of the overall process. You are saying that it is acceptable that the process can execute only if its working set is present in the memory. And what you have to do is, so whichever pages are not present in the working set, whichever pages are not present in the working set, that you have to remove, swap out. What can be the issue in case of in case of working set method? What can be the issue? One issue is very simple: past does not always predict the future, right? So you are relying on the past, you are relying on the principle of locality, that whichever pages are referenced in past, those pages I am referring, and those pages I am keeping in working set. But it may be possible that your process is not reflecting its past and is changing its references. So at that time, this method is failed. Also, you have to kind of include the overhead of measurement of working set, and finding an optimal value of delta is also difficult. So these are the issues of working set. Because working set principle is very simple. At every point, you are looking at the past few references of the process. At every point, you are looking past few references of the process, and based on that, you are swapping out the other. You are based on that, you are swapping out the other pages. So, if past does not reflect the future, it will be difficult. And one more approach is, instead of focusing on the past, you can focus on the page fault rate of the process. So what is the meaning of page fault rate? It means whether the page that you are referring for the process, whether the page that you are referring, can you find it from the memory or not? So what you do is monitor the page fault rate. If the page fault rate is above the threshold, it means that if the page is generating lot of page faults, okay, if the page is generating lot of page faults, then what you have to do? You have to increase the size of the residence set. Right? You have to increase the size of the residence set so that more pages are present in the residence set, and due to that, the page fault rate will drop. Also, the other possibility is, if the page fault rate is below some threshold, then the residence set size should be decreased. Means that if some page is not generating page fault at all, then you can decrease the residence set size. So this is just a illustration of the algorithm, page fault frequency algorithm. And the last thing is cleaning policy. What is the meaning of cleaning policy now? See, the cleaning policy is concerned with determining when a modified page should be written out to a secondary memory. So see, what happens is, some pages are there in the main memory which are modified by the user. User has modified them. Now those pages, because they are modified, you need to write the changes back to the disk. Right? You need to write the changes back to the disk. So one of the option is demand cleaning. So meaning of demand cleaning is that whenever the page is to be swapped out, or whenever the page is selected for the replacement, at that time you have to write that page to the disk. At that time you have to write that page to the disk. So in that case, you require two things. First, you have to write the dirty page. Dirty page means modified page. And second, you have to read the new page. So it is kind of costly, because demand cleaning, we have also seen demand paging. So demand means that whenever something is required, you do it at that time only. Other is pre-cleaning. Other approach is pre-cleaning. So pre-cleaning approach, in that pages are written out in batches before their frames are needed. Right? So this is kind of more proactive and more optimized. So in pre-cleaning, what you do, as soon as you find a page that is modified, that needs to be written out to the disk, you immediately do it. Don't wait for it to be replaced. Right? No need to wait that, okay, when it will be replaced, I will do the cleaning. So pre-cleaning is like that. And load control, what is load control? So load control basically determines number of processes that will be resident in the memory. Is the level of multi-programming. If you recall, we have discussed it while looking at the process scheduling. So whichever number of processes are there in the memory, that is called the multi-programming level. If there are too few processes, then many processes will be in block state and much time will be spent in the swapping. So processor uh, will be basically uh, idle because only few processes are there and many of them will be blocked. So processor will be idle. On the other hand, if there are too many processes, then what will happen? It will lead to thrashing because too many processes are there. So when they require swap in, swap out, most of the time of the processor will be spent in swap in, swap out rather than doing the actual execution. So this is the idea of multi-programming level. So as the multi-programming level is less, processor utilization is also less. But as you increase the multi-programming level, processor utilization saturates. And then again, if you increment, it will basically drop. So again, see, it's all about finding this optimal point. So conclusion is that neither the less amount or nor the more amount. You have to find the ideal amount of multi-programming, right? And last discussion is on process suspension. Which processes you suspend? So these things we have already discussed. So lowest priority process, then halting process, then process which is activated for the long time, process with the smallest precedence set, largest process, and process with the largest remaining execution window. So these are some of the reasons for process suspension. But this we have already discussed while discussing the process in detail. Okay, so that's all for this chapter. It's a long chapter. So many theoretical points are included, and most of them are kind of rules or policies which your operating system must support. So, is the end of the chapter. From next time, we are going to start a new chapter that is based on the process synchronization and deadlock. So that will be our new chapter, which will start from the next lecture. Meanwhile, for today's lecture, if you have any queries, you can ask me or we can close the session. Okay, so let's end the session.